Hi, nice to meet all of you. My name is Carson Lam, and what I want to do for you today is give you something that I think is harder for you to find for yourself, which is I think that all of you are interested in this ChatGPT machine, and it's a very large, complex machine. And so I want to show you a version of that that's very small, simple, self-contained, so you can fit it in the palm of your hand and take a look at it, take it apart, and I want to do that for you because that's how I learned the best, and I think that many of you probably learned that way too. Several years ago, I was actually a practicing ophthalmologist, and today I lead a team tackling machine learning problems, and so that's a big jump. And the only way I was able to do that is I was willing to stare at things that uncomfortably made me feel like I didn't understand any of it for a long time, and I was willing to revisit that later on. And that's what I'm going to do for you here today. A lot of these things in this talk you're not going to understand the first time around, but don't worry, there's no test on this afterwards. So all I expect from you is just to be open and just take from it what you can. And if you're doing that, you're doing your best, and you have nothing else to worry about. So let's get started.
Okay. Will ChatGPT do X? Question mark. Build your own mini ChatGPT and then decide for yourself. So what I want to share with you today is a focused dissection of the implementation details of a small, simplified, self-contained toy project demonstrating reinforcement learning from human feedback with special emphasis on connecting the equations describing proximal policy optimization to the lines of PyTorch code that apply PPO to work with sequences, such as completing sentences so that they end with a positive sentiment. We do this not by self-supervised or supervised learning, but rather by letting the model generate text on its own and learn from scores assigned to that text after it is generated. This is analogous to the way ChatGPT was trained using human scores of model-generated answers to instructions. We end by discussing what we know so far about the properties that emerge as these models are scaled up. My name is Carson Lam. I'm a machine learning engineer. I lead the AI team at a startup called Carrot Coach. We provide home health aid to persons with special needs using our technology. With regards to this talk, an even more detailed version of this tutorial in the form of Jupyter notebooks can be found at my GitHub at this link here. It has links itself to better explanations of a lot of these concepts in case a lot of this passes you by and not able to capture it in this talk. You can always revisit it. This work borrows heavily from the work of Leandro von Juarez, TRL repository that has been improved by Hugging Face engineers. And the TRL repo on GitHub itself is based on the OpenAI's baselines repo. I also take several figures in various from various blogs and scientific publications mentioned here. Lastly, some of the people I take inspiration from and have to thank for their simplifying of AI concepts for thankful students like myself, Andre Karpathy and Chris Ola. Okay, first let's define some terms. First, in this talk, when I say transformer, large language model, foundation model, agent, and policy, I mean the same thing. And when I say that generate text, emit a token, sample from a distribution over the vocabulary, take an action, I also mean the same thing. Most tutorials on reinforcement learning today describe the process of reinforcement learning as an agent reacting to the state of its environment by taking an action, observing a reward and change to its state, which presumably was affected by a past action. Then, over the course of many of these state action reward sequences, learns a policy for how to act that maximizes the reward over some predefined time horizon. In reinforcement learning from human feedback, for text generation, the state or environment is the input prompt, such as the instructions to ChatGPT or the incomplete beginning of a sentence. The action is how the language model chooses to respond to those instructions or what tokens the model samples in order to extend the sentence. In the example above, suppose our language model has a tiny vocabulary of size 9 possible word tokens. The green fourth bar down corresponding to token ID equals 4 is the word cat. The tool that helps us go back and forth between the integer 4 and the string cat is called the tokenizer. When the model is prompted with the incomplete sentence, I saw A, with the last token the last token A induces the model to output a probability distribution over all of its vocabulary. The length of the bar represents the probability assigned to the word cat. During pre-training, every time the word cat comes after I saw A, the cross entropy function updates the model to increase the probability assigned to cat. So reinforcement learning is a different way to update the same model because, of course, there are many valid ways to complete a sentence, to answer an instruction, and there are also many invalid ways to do these text completion tasks. Instead of using a cross entropy loss function, which is analogous to asking the model to memorize many sequences and then interpolate between what is learned, which can still do amazing things, as most of us here know already, we elicit the model instead to using a prompt to generate a new sequence of tokens and then assign scores to those completed sequences. Reinforcement learning is about designing training processes to update the model to effectively maximize those scores. So this process is outlined in step 3. And so step 3 is what this talk will focus on. Because there are already so many ample resources explaining step 1 and step 2, which uses standard self-supervised language modeling techniques, such as predicting the next token in a static data set, or in the case of reward models, uses supervised learning from human labels. Okay, so let's start building. First, the data set. The data set is like a large collection of sentences, in this case, or in ChatGPT's case, a large collection of instructions. But we're going to start small, so we're just going to do incomplete sentences here. Usually these sentences are larger than 8 tokens long. So it means that if we take the first 2 to 8 tokens, we will have the beginning of an incomplete sentence that we can use to prompt our policy to generate the rest of the sentence. Next, we initialize the language model that we will update using reinforcement learning from human feedback, RLHF. We'll call this the new policy. That's the one we update. And we'll also hold on to a static version of the original pre-trained model called old policy. And then a tokenizer that maps between integer IDs and their corresponding substrings. Remember, for us, taking an action means outputting a probability for each token, then choosing one of those tokens to be our next token, using that token to extend the sequence by 1, and repeating the whole process again until we, for example, hit a stop token and then we know to stop generating forward. If you always choose the most likely token, that's called a greedy strategy. We are not going to do that. We are setting the do sample argument to true in order to generate a diversity in our actions. So it's stochastic, essentially, the way that we're going to generate. We will take 4 to 16 steps into the future. In other words, we will extend the prompt by 4 to 16 tokens before we assign a score to the final sequence using a reward model. Next, the PPO trainer turned our dataset into a data loader, which is an iterator that I can repeatedly ask to give me batches of starting prompts. I would consider this data loader to be analogous to the environment in the sense that the start prompts or the beginning of sentences are kind of like states in typical RL. It keeps presenting new states and eliciting new actions from the policy. You will see that in the Mini-ChatGPT repo, these start prompts are called queries. The text version is displayed here, along with below it the token ID version of the same queries. And those IDs are what are inputted to the model. So these queries are then fed to the policy to generate the rest of the sentence. Gen length means generation length. It's a number between 4 and 16 that will tell the method called generate how many tokens to extend by. Printed out are the new token IDs generated by the new policy, which we call responses. Below, I have used the tokenizer to decode both queries and responses back into text, and then put them side by side, separated by this special symbol to make it more clear and confirm what's happening. So take note that there are 4 sentences in this batch. So our reward model assigns a score between a desirable +2 and an undesirable -2 to each of the 4 sample sentences. And now with these queries, responses, and rewards, analogous to state action rewards, we perform one PPO step, update step. But before we zoom into the PPO step, let's zoom out and put everything into context before we get lost in the details. Okay, so on the left here, the code. All I've done here is placed those same lines of code that I've already shown you, but I've placed them into a for loop. And with each iteration, I collect the average of the rewards into a list called rewards list, and then plot those average rewards for each batch in orange in the plot to the right. And if you try this yourself and print out the sentences like I did in the previous slides, as you go along, you'll notice that they get more and more positive sounding with this approvally quality to their sentiment as you watch that orange line go up and to the right. I will go over what returns are when we dive into PPO. And the next slides, just so you know, they all take place within the PPO trainer .step function. There are other RL algorithms to use besides PPO, but whichever one you choose, you probably have some risk of distributional collapse. That's when RL updates cause the model to deviate so much from its initial pre-training that it starts to speak nonsensically, or in physical environments, for example, forgets how to walk, jumps off a cliff, learns these undesirable policies, thus adding noise to the training and making things worse and getting in the way of improvement. A technique usually found in RLHF used to avoid distributional collapse is KL regularization, or a KL penalty on the reward. On the left is equation 2 from the fine-tuning language models from human preferences paper. In this equation, X is the prompt, Y is the generated sequence, pi is the distribution of the new policy, rho is the distribution of the old policy, beta is a scaling term that is adjusted during training to incentivize the KL divergence. The Kolbeck library, I'm butchering that name, but the KL divergence between pi and rho to be some target that the experimenter chooses. For example, targeting a KL divergence of 6 nats, where nats is the measure of KL divergence, the difference between the 2 policies or distributions. The corresponding Python implementation of equation 2 is below it. Recall that log of A over B is the same as log A minus log B. When you take the expectation of equation 2, you get the expected rewards minus the KL divergence. The formula and corresponding code for the dynamically adjusted beta term is on the right, and I'll show later how we got the log probabilities from our new and old policies, but I want to give you the motivation of why we do this first. Notice that the first time this is calculated, the non-score reward, or the KL penalty, is 0, and that's because the new policy has not been updated yet, and so it's still identical to the old policy. And the final reward is just placed into the last position of the sequence for each of the 4 sentences. Okay, so to clarify the code for getting log probabilities, or log probs, I borrowed this figure from the Lambda paper, the one on the bottom left with the blue boxes. Notice that the sequence in the top row is the same as, but just one position behind the sequence on the bottom row. And that's because what is implicit in the diagram is that the blue boxes represent hidden states, also called vector representations, which in the top diagram is represented by a pink vector H. The hidden states of the deepest or top layer in the blue diagram also go through a linear layer that transforms the hidden state into a vector with a logit for each token in the vocabulary. These logits are pushed through a softmax layer so they can be interpreted as the token probability, at the token probability distribution. We sample this distribution at the top of one column, and that becomes the token at the bottom of the column just to the right of it. And you'll see in the code snippet on the lower right that the function f dot log softmax is used to transform the logits output from the policy directly to log probabilities. Also notice the way the logits are indexed different from the input IDs or the token IDs. The colon -1 and the 1 colon for the input IDs. That's because in the blue diagram, the logits that the token in step T is sampled from come from the logits at position T -1. Okay. Next, we're going to jump to the topic of advantage functions. There's already plenty of explanations of this topic with respect to reinforcement learning, and it's not specific to RLHF, so I'll only briefly describe it for the sake of clarifying why the code is written the way that it is. In simple terms, it's because it is noisy which actions lead to which rewards. When you define the direction and magnitude of benefit of your actions, it's better to use the difference between what I'm going to call Q minus V. So Q is the total rewards you think you got from taking this action in this state, whereas V is the total rewards you think you would get just from being in this state, averaged over all the actions you could take, including the one that you did take. In the equations at the bottom that all start with capital A equals, it's useful to group everything to the left of the minus sign into one term and everything to the right of the minus sign into another term, which is to the right of the minus sign, it's just capital V all the time. To the left, we'll call that Q, and Q has different versions. For example, R sub T plus V of S sub T plus 1 is a slightly more detailed estimate of the returns, because what R sub T means is it's the reward that we actually received immediately after taking action A sub T. And actually, you could make this more and more detailed by including more R terms in the future. And arbitrarily, until the end of the sequence, or end of the episode, obviously. I will refer to this as the short range versus long range estimates of return, or the discounted rewards into the sum of discounted rewards. That's the returns. The problem with longer range estimates is that you don't really know if the current action is what led to those future rewards or punishments. It could be a state in the past or future, or a combination of actions. So the generalized advantage estimation strikes a balance between the long range and short range estimates of returns by calculating an exponentially weighted moving average, the EWMA, for the advantage. The lambda is a weight parameter that, when higher, incorporates more of the non-immediate rewards into your estimate. The summation expression above is basically the formula used to calculate EWMA, which, if you follow the math, and there's more on this in the GitHub repo, in case I'm going too fast. But basically, the expression here says that you can start by calculating the advantage of the very last time step, or the very last position in the sequence, in other words. The symbol delta is used to mean the advantage at a specific time step, rather than a capital A, which is the EWMA version of the advantage that is a combined version of all these different estimates overall using lambda. I'll say this again. So we use the advantage at the T plus 1 position to calculate the advantage at the T position, and we use the advantage at the T position to calculate the advantage at the T minus 1 position, and so forth until we get to the first position in the sequence. To help you when you study this on your own, I have put the mathematical equations above and the corresponding operations expressed in PyTorch code right below it. Another thing we need to do is, because we use this estimate based on the state of the returns, called the value function, we need to continually improve our value estimator function as we train. And we do this by comparing the actual returns with our estimate and minimizing the squared error loss between them. This implementation detail is not explained in detail in the PPO paper, but when you look at the discussion in the OpenAI baseline repo, the authors state that they, quote, clip the value function objective to reduce variability during critic training. So here, the word critic means the value function. So similar to the surrogate clipped loss we are about to discuss next, they also clip the value function loss, and you'll see why clipping works in the next slides. Okay, so this method of stabilizing training is at the center of PPO, and it's called the clipped surrogate objective. Before I show the usual equations and code, let's just go through an intuitive explanation of the equation and what this equation and code does for us. What we will do is that for each of the actions our policy takes, we compare the probability of taking said action by the new policy with the old policy. And we represent this comparison using a ratio between the two, where the new policy is on top in the numerator and the old policy is on bottom in the denominator. So in order to disincentivize these radical, noisy, unconstructive updates to the new policy, we update our policy only if, and by the way, this comes from the Hugging Face blog on reinforcement learning. We update only if, one, our ratio is in the range 1 minus epsilon to 1 plus epsilon. So for example, if epsilon is 0.2, the range is 0.8 to 1.2. Or the other situation, two, our ratio is outside the range, but the advantage leads to getting closer to the range. So there's two cases of this. The ratio is below the range, but the advantage is positive, so greater than 0. Or the ratio is above the range, but the advantage is negative or less than 0. So here's the equation on top and the code on bottom that that behaves as we have just discussed. Keep in mind the minus sign is in front of the advantage, so that flips the min operation to a max operation, and also that e to the power of natural log pi new minus natural log pi old is equal to just the ratio pi new over pi old. The expectation term means that we're going to take the average over several steps and several sequence samples. And just to emphasize again, r theta sub t is the ratio. It's not the reward. It's the ratio between the new policy and old policy. And for example, when the ratio is 1, it means they're the same. They're the same policy with respect to this particular action and state. And a ratio of less than 0.8 or greater than 1.2 means that the new policy is very different from the old policy by a factor of 0.2 in this example. Okay, so this is the combined PPO objective composed of 3 parts. There's the policy gradient part, the value function part, and lastly, the entropy part. The TRL authors leave out the entropy term because it didn't seem to help very much, and so they just decided to leave it out. At least at this point, we haven't figured out a good way to make it beneficial. And so, which is why in our case, when you see after we return the policy gradient loss and value function loss from the function above, the final loss that we back propagate on is this loss equals PG loss for policy gradient plus coefficient times VF for value function loss. And we maximize this objective, which is why there's a negative term in the expression in this diagram here for the squared loss, because if you maximize the negative of this component, it's the same as minimizing the component. Okay, so let's end off by zooming back out and looking forward to the future. So maybe some of you are disappointed that the Mini-ChatGPT was more mini than you had anticipated. Like for example, you asked it to write your midterm paper on the mating patterns of Gen 2 penguins, and it did not deliver very well. In the diagram to the left, though, you'll see that there's a distinct phase transition that occurs at certain levels of scale. Scale is measured here in training times parameters. And abilities mean things like few shot prompting, for example, that emerge unexpectedly and quickly as you gradually move up the scaling ladder. Research is still happening, but as far as we can tell, the same synergies between scale and few shot, for example, should still be true of RLHF, in that RLHF bestows a distinct change onto the model that is different from doing, cross entropy training on more examples of positive sentiment sentences, for example. On the diagram to the right, it's from Anthropic's paper. We see one of their papers. We see that with respect to human preferences, it can sometimes achieve rewards that otherwise would require a model to be 2 orders of magnitude larger in terms of parameters with current methods. It's possible. So the question of is it possible, and how do you anticipate these emergent abilities is a bit more complicated. You can't simply extrapolate from how a smaller model is improving because they're unexpected. But but it is being researched. Like for example, one promising area is the study of this phenomenon called grokking. And so I'll just end by reading you a quick part from that paper. The bottom paper's result shows that grokking, rather than being a sudden shift, arises from the gradual amplification of structured mechanisms encoded in the parameters, followed by later removal of memorizing components. So training that they say training has 3 continuous components. First happens a memorization phase, and then a circuit formation phase, and then a cleanup phase where you erase out the memorization parts of the model, and then at that point you see this emergence in the model. Okay, thank you very much. Bye bye.